at a drop falling on a water surface. The water molecules behave in a collective way, forming center-symmetric waves. Or look at the two pendula. Each pendulum alone would oscillate in a regular way. The coupled pendula can have a quite chaotic and almost unforeseeable motion. Or think of individual atoms. For example, take two atoms with two different energy levels, like carbon and oxygen. When you bring the atoms together, the two levels interact and might form a bonding and antibonding state. The properties of the molecule are very different.
So we can easily solve Schrödinger equation for the hydrogen atom, but when we talk about the complicated many electron problem, the Hamiltonian things are getting difficult, and it is very difficult to solve the Schrödinger equation, time independent Schrödinger equation. So the question arises, why we need to study the many body system? Because in order to model the materials in the computer, we have to study about the behavior of the atoms and the electrons. And how we can study the behavior of atoms and electrons? By solving the Schrödinger equation, because normal physical laws don't work at this level. Consider the electrons represented by the I and J in the diagram, and the nuclei represented by A and B, capital A and B in the diagram. The lines are the shows the interaction between the nuclei and the atoms. We can write the wave function for that, representing the position of the electrons with the x1, x2 up to xn, and the position of the nuclei with the r1, r2, r3 up to rm. When we write the Hamiltonian or the Schrödinger equation for this many body system, we arrive at the kinetic energy of the electrons, the kinetic energy of the nuclei, the Coulombic interaction between the nuclei and the electrons, and the Coulombic interaction between the between two electrons and between two nuclei. And here we are using the atomic units in order to simplify our problem. The original equation of the Schrödinger is very difficult to solve because of the complexity, but we can approximate the equation with the following with the approximation. The first one is the Bohr-Oppenheimer approximation. In the Bohr-Oppenheimer approximation, it is stated that the masses of the nuclei are very heavier than the electron. So as compared to electron, the nuclei are moving very slowly. So we can neglect the motion of the nuclei, and we can consider the nuclei as the parameter rather than a variable. When we fix the position of the nuclei, the kinetic energy of the ions become 0, and we are treating the Coulombic interaction between the nuclei as the constant. As the constant has no preference in the Hamiltonian, means it has no effect on the Schrödinger equation. So all we obtain is certainly an electronic Schrödinger equation. Now we have to solve the electronic Schrödinger equation, but still it is difficult due to the presence of the electron-electron interaction. We need further approximation to solve our problem. So how we solve the many body problem? There are many approximations like in physics and in the chemistry. Different methods are used for this, but we will start our discussion with the Hartree approximation and Hartree approximation. So let us discuss about the one electron problem. Consider an electron, like we have discussed, we have presented like hydrogen atom, that one electron like hydrogen atom, in which one electron is revolving around the nucleus. So what the variation principle states, Variation principle state that we can try the multiple we can try the multiple wave functions, and the one that gives the lowest energy, that is our ground state wave function. So we are interested in the ground state energy because and the variation principle is applied to the ground state energy. So for when we talk about the one electron, we can um, write the uh, so
So the question is why we are interested in the ground state energies, because the most observables are come from the ground state, and like structure, bonding, magnetism, they are all the ground state properties, and the ground state is the one that define the equilibrium structure. Um, and it is a variational principle. When we talk about variational principle, it is only valid for the ground state. For the excited state, it is slightly harder.
solving Schrodinger equation for the one electron is similar to the solving the variational principle, because we solve the Schrodinger equation to find the minimum energy, the ground state energy, and the variation principle said that we are trying the different wave functions, and the one which give the minimum energy will be our solution. So both have the same idea. So if we try to solve the variation equation, that means we are trying to solve the Schrodinger equation. So when we let's discuss it for the one electron problem. We can write the one electron problem. One electron Schrodinger equation contain the kinetic energy and the potential energy. We can write it in the functional form as seen here. So it depends upon the orbitals. Applying the solving the Schrodinger equation for the one electron problem, we come for so it is very difficult to take one function and normalize it, and then evaluate the energy and find whether the energy is low or minimum. That is a huge complicated task. The idea is that we can we know that for the one electron or for the hydrogen atom, the Schrodinger equation has a solution. So if we join all those atoms, that is we join all those one electron problem, so their solutions can give us the linear combination of the solutions of the already known wave functions can give us the solution for the new problem. Like we have a trial wave function, whose solution is unknown. So for that trial wave function, we can write that trial wave function in the superposition of the many other wave functions for which we know the solution. But um, these are we can the problem here is that we can construct the wave functions. We can construct the trial wave function and apply the variation principle on that, and find the energy. But this is really a guess to find and in the real world the guess don't work. With the more practical idea, we can use the functional derivatives. Functional derivative is the finding the variation in the function upon changes in the function as a linear combination of the local changes. So we have to minimize the we have to find the f functional um, which is equals to the kinetic energy, the potential energy, and a constant. We can easily find the we know that the minimum energy is the one whose derivative will give us the zero result, because minimum energy at the minimum at the minimum the derivative is zero. So the kinetic energy is defined. Kinetic energy, the potential energy, and the constant can easily be their functional derivative can easily be taken. and from there and from all this putting in the Schrodinger equation we can find the constant. So in that way using the real wave function and applying the variational theorem to find the minimization of energy, minimum amount of energy, the functional derivative make it possible. This is how the one electron problem can be solved. Further talking about the two electron problem, uh, we have the Pauli exclusion principle come into the play because these two electrons will be in the ground state in the single state for that spin is equals to 0. So one have to be in this spin up position and one have to be in the spin down position. So the real wave function consists of the two parts, the special part and the spin part. The special part will be symmetric while the spin part will be anti-symmetric, and the product of the symmetric and anti-symmetric will give us the anti-symmetric wave function, and this is all we need to continue further, because to work with the wave function, trial wave function, it must be normalized and it must be anti-symmetric. Finding the energy wave functional. Now we have to find the energy functional for the two electrons, and we can easily do this with the variation principle as we discussed. Here the kinetic energy and the potential energy terms are the one electron functional as we discussed a few minutes ago in the couple of slides. The electron to electron potential, it is difficult to consider individual electrons and find and consider each individual electron interact with the other electron. So Hatry represent the average effect potential that an electron experience from the density of the all other electrons, that make a problem simpler. Here the exchange term is not included because we have only two electrons and they are in this and they have the opposite spin. Exchange terms come into play when there are same spin states.